Hello, welcome students. Here in 8th part of the video, we will discuss colligative properties. And in this part, we will discuss mainly two topics, relative lowering of vapor pressure and elevation in boiling point. First of all, colligative properties. The properties of the solution which depend only on the number of solute particle but not on the nature of solute are called colligative properties. It means the colligative properties are such properties which depends only on the number or the amount of solute particle which is dissolved in solvent and does not depend on the nature of solute particle. So such properties are known as colligative properties. Now there are mainly four types of colligative properties which we have to learn. First is lowering of vapor pressure. Second is elevation of boiling point. Third one, depression of freezing point. And fourth is osmotic pressure. These are four colligative properties which we have to learn in this video. And among these four, we will basically learn these two. One is lowering of vapor pressure and elevation in boiling point. First is relative lowering in vapor pressure. So as we have already learned in our previous topics that when a non-volatile solute is added to a solvent, the vapor pressure of the solution gets decreases. अगर हम कोई नॉन वॉलेटाइल सॉल्यूट को ऐड कर देते हैं सॉल्वेंट में तो जो पूरा सॉल्यूशन है उस सॉल्यूशन का वेपर प्रेशर डिक्रीज हो जाता है. क्यों? क्योंकि सॉल्यूशन की जो वेपर्स हैं ऑन एडिंग अ नॉन वॉलेटाइल सॉल्यूट वो कम फॉर्म होने लगती है. एज द वेपर्स फॉर्म लेस सो द वेपर प्रेशर गेट डिक्रीजेस. नाउ द वेपर प्रेशर ऑफ द सॉल्वेंट इन सॉल्यूशन इज ऑल्सो लेस देन द प्योर सॉल्वेंट. इट मीन्स जो सॉल्वेंट अब सॉल्यूशन में प्रेजेंट है मीन्स जो सॉल्यूट के साथ ऐड वाला जो सॉल्वेंट है जो सॉल्यूशन में जो सॉल्वेंट प्रेजेंट है उसका वेपर प्रेशर लेस होगा देन डेट ऑफ द प्योर सॉल्वेंट. अगर हम प्योर सॉल्वेंट के वेपर प्रेशर की बात करते हैं तो प्योर सॉल्वेंट का वेपर प्रेशर एंड जो सॉल्वेंट सॉल्यूशन में प्रेजेंट था उसके वेपर प्रेशर को अगर हम कंपेयर कर रहे हैं तो जो प्योर सॉल्वेंट का वेपर प्रेशर है डेट विल बी हायर as compared to the vapor pressure of the solvent which is present in the solution. Now from this let us consider the following terms. Let x1 be the mole fraction of the solvent and x2 be the mole fraction of the solute in the solution, and P1 naught is the vapor pressure of the pure solvent, where P is vapor pressure of the solution and P1 will be the vapor pressure of the solvent. So if we suppose these points where P1 naught is the vapor pressure of pure solvent when vapors are present in pure form, it means when we have only the solvent in our container, when we have only the solvent, then the pressure due to these solvent molecule that will be denoted by P1 naught, प्योर वेपर प्रेशर ऑफ द सॉल्वेंट. बट जब हमने मिक्स कर दिया उस सॉल्वेंट में हमने मिक्स कर दिया सॉल्यूट पार्टिकल, प्योर सॉल्वेंट था, हमने इस प्योर सॉल्वेंट में हमने मिक्स कर दिया कुछ सॉल्यूट पार्टिकल भी मिक्स कर दिए यहाँ पे आके. जैसे ही हम सॉल्यूट पार्टिकल्स को मिक्स करेंगे तो अब जो सॉल्वेंट की वेपर है और सॉल्यूट हमारा कैसा है नॉन वॉलेटाइल, उसने तो वेपराइज होना ही नहीं है सॉल्यूट ने, केवल क्या वॉलेटाइल होगा सॉल्वेंट के मॉलिक्यूल्स वॉलेटाइल होंगे. अगर केवल सॉल्वेंट के मॉलिक्यूल्स वॉलेटाइल होने हैं तो लेकिन आ तो गया नॉन वॉलेटाइल सॉल्यूट. नॉन वॉलेटाइल सॉल्यूट जो वर्क करेगा वो क्या करेगा, रिड्यूस कर देगा फॉर्मेशन ऑफ वेपर्स ऑफ प्योर सॉल्वेंट. जो वेपर जो फॉर्म हुई थी इस वाले में जो बहुत सारी वेपर्स फॉर्म हो रही थी सॉल्वेंट की, वो सॉल्यूट ऐड करने के बाद वो सॉल्वेंट की वेपर्स क्या हो जा रही है, डिक्रीज हो जा रही है. और इस कंडीशन में जो वेपर प्रेशर है सॉल्यूशन का उसको हम डिनोट करेंगे किससे, पी से. अब ये जो वेपर प्रेशर कहलाएगा किसका कहलाएगा, सॉल्यूशन का कहलाएगा, और इसको हम डिनोट करेंगे पी से. और यही वेपर प्रेशर किसके इक्वल होगा, क्योंकि केवल किसकी वेपर्स ऊपर फॉर्म हो रही है, केवल सॉल्वेंट की. सॉल्यूट तो हमने ऐड करा है, वो क्या है नॉन वॉलेटाइल इन नेचर में सॉल्यूट ऐड करा है, बट इट इज नॉन वॉलेटाइल इन नेचर, बट द वेपर्स विच आर प्रेजेंट इन द वेपर फेज इज ओनली due to the solvent molecules. So the vapor pressure of the solution, which is denoted by P here, will be equal to the vapor pressure of the solvent which is present in the solution, and which is denoted by P1 here. So this can be clear from this also. Since solute is non-volatile, so there will be no contribution of solute to the vapor pressure. Due to this, P1, the vapor pressure of the solvent, will be equal to the vapor pressure of the solution. Now as we solve this, so according to Raoult's law, the vapor pressure of the solvent P1 will be equal to vapor pressure of pure solvent P1 naught into its mole fraction. This is Raoult's law. Now the reduction in vapor pressure of the solvent, that can be shown as delta P1. So what will be the value of delta P1? Delta P1 will be equal to vapor pressure of pure solvent minus vapor pressure of solvent when it is present in solution, because as we have already mentioned that the vapor pressure of pure solvent is higher than the vapor pressure of solvent when it is present in solution. Why it is so? Because when the solvent is present in its pure form, the vapors of the solvents are forming in more amount as compared to when the solvent is present in its combined form. When the solute get mixed with solvent, then the vapors of solvent get reduced. So as we denoted the reduction in the vapor pressure of solvent, so delta P1 will be equal to P1 naught minus P1. Here also, on putting the value of P1 from Raoult's law, what we will get delta P1 will be equal to P1 naught minus P1 naught into x1 on putting the value of P1. Now taking P1 naught as common, we will get equation A. As we know that x1 plus x2, mole fraction of two component, x1 plus x2 is always equal to 1. So here from here x2 equal to 1 minus x1. So as we know that x2 equal to 1 minus x1, so now putting the value or of x2 in equation 1, what will we get? We will get delta P1 equal to P1 naught into x2. This will be equation B. In the solution containing several non-volatile solutes, the lowering of vapor pressure depends on the sum of the mole fraction of different solutes. So from equation B, on rearranging equation B, as we put the pressure terms on one side and the mole fraction in other side, we will get this equation. Delta P1 upon P1 naught will be equal to x2. That will be equal to mole fraction. Now, since delta P1 will be equal to P1 naught minus P1, as we have discussed earlier that delta P1 is reduction in vapor pressure, and reduction is vapor pressure equal to vapor pressure of pure solvent minus vapor pressure of solvent when it is present in solution. So P1 naught minus P1 upon P1 naught equal to x2. Now this P1 naught minus P1 upon P1 naught, this expression is known as relative lowering of vapor pressure. Thus, the relative lowering of vapor pressure of an ideal solution containing the non-volatile solute is equal to the mole fraction of the solute at given temperature. So this is the expression for relative lowering of vapor pressure. Now, from the relative lowering of vapor pressure, we can also determine the molar mass of the solute. So the determination of molar mass of solute from relative lowering of vapor pressure, from this equation C, here x2 is present. x2 means mole fraction, and the value of mole fraction of solute will be equal to number of moles of solute, that is N2 divided by number of moles of the solution, that is N1 plus N2, where N1 is number of moles of solvent. This is for solvent. and N2 is number of moles of solute. This must be clear that we are using 1 for solvent and 2 for solute particles. So as we all know that number of moles is equal to mass of the compound divided by molar mass. So number of moles of solvent will be equal to mass of solvent divided by molar mass of solvent. Similarly, number of moles of solute N2 will be equal to mass of solute W2 divided by molar mass of solute M2. Now here N1 and N2 are the number of moles of solvent and solute respectively present in the solution. So for a dilute solution, अगर हमारे पास में सॉल्यूशन हम डाइल्यूट लेंगे तो डाइल्यूट सॉल्यूशन का जो कैरेक्टरिस्टिक है वो यही होती है कि डाइल्यूट सॉल्यूशन में सॉल्वेंट का अमाउंट ज़्यादा होता है और जो सॉल्यूट है उनका अमाउंट कम होता है. ये हमें अच्छे से पता है. अगर हमारे पास में सॉल्वेंट का अमाउंट ज़्यादा होगा, व्हाट डज इट डिनोट्स? इट डिनोट्स दैट N1 शुड बी ग्रेटर देन N2. मतलब नंबर ऑफ मोल्स ऑफ सॉल्वेंट जो होंगे वो बहुत ज़्यादा होंगे एज कंपेयर टू नंबर ऑफ मोल्स ऑफ सॉल्यूट फॉर डाइल्यूट सॉल्यूशन. सो एज दिस इज द सिचुएशन, सो द we can neglect N2 in the denominator, means we can neglect number of moles of solute in the denominator. So as we neglect, then we get the equation and we will get that P1 naught minus P1 upon P1 naught, that is relative lowering in vapor pressure, equal to number of moles of solute divided by number of moles of solvent. On putting the values of N1 and N2 to this equation, we will get this. Hence W1 is the mass of solvent, as we have already discussed. W2 is the mass of solute, and M1 is molar mass of solvent and M2 is molar mass of solute. So from relative lowering of vapor pressure, we can easily find that the molar mass of solute, the value of molar mass of solute, that is M2. On putting these values to this equation, we can easily find out the molar mass of solute from relative lowering of vapor pressure. So one question is there. A solution is made by dissolving 30 gram of a non-volatile solute in 90 gram of water. So amount of solute is given, weight of solute is given, that is 30 gram, and it is dissolved in 90 gram of water. It has a vapor pressure of 2.8 kilopascal at 298 Kelvin. At 298 Kelvin, vapor pressure of pure water is 3.64 kilopascal. Calculate the molar mass of the solute. Now, according to relative lowering of vapor pressure, we know the formula. Given is weight of solvent, that is 90 gram, weight of solute 30 gram, molar mass of solvent 18, because solvent is water, so molar mass of water is 18, and we have to find out the molar mass of solute, that is M2. Now on putting these values, as we know that the pressure of pure water pressure of pure water is 3.64 kilopascal, that is P1 naught is equal to 3.64 kilopascal, whereas vapor pressure of solvent when it is present in solution, that is also given, and value of P1 is equal to 8.2, which is the vapor pressure of the solvent when it is present in solution. So on putting these values to the equation of relative lowering of vapor pressure, we can easily find out the value of M2 here. So on solving the equation, M2, the molar mass of the solute, will be equal to 26 gram per mole. Now there are some practice questions related to the topic relative lowering of vapor pressure. Now the second colligative property is elevation in boiling point. Since the boiling point of a liquid is the temperature at which its vapor pressure becomes equal to atmospheric pressure. मीन्स बॉइलिंग पॉइंट वो पॉइंट है, वो टेम्परेचर है बॉइलिंग पॉइंट किसी भी लिक्विड का जहाँ पे उसके वेपर प्रेशर इक्वल हो जाते हैं एटमॉस्फेरिक प्रेशर के। कोई भी लिक्विड है बॉईल होना स्टार्ट हुआ और जैसे ही उसकी वेपर अपने वेपर फेज में गई, एक टेम्परेचर ऐसा जनरेट होता है जहाँ पे वेपर फॉर्म होने से जो वेपर प्रेशर था वो इक्वल हो जाता है एटमॉस्फेरिक प्रेशर के। तो दैट पॉइंट इज नोन एज बॉइलिंग पॉइंट। ठीक, since the vapor pressure of the solution containing non-volatile solute is less than that of the solvent, as we all know that as we have a non-volatile solute, so the vapor pressure of a non-volatile solute is always less than that of the solvent. So the solution has to be heated to a greater temperature so that its vapor pressure becomes equal to its atmospheric pressure. If we are talking about boiling point, and as we added non-volatile solute to the solvent and a solution is formed on adding solute to the solvent, what will happen? At that point, since solute is non-volatile, so the vapor pressure of solute is less as compared to the solvent. And as the vapor pressure of solute is less as compared to solvent, then the vapor pressure of the solution also get decreased. So as to increase the vapor pressure of solution up to its atmospheric pressure, we have to heat, we have to provide temperature to the solution. क्योंकि नॉन वॉलेटाइल सॉल्यूट ऐड करने पे तो वेपर प्रेशर डिक्रीज हो गया, सॉल्यूशन का ही वेपर प्रेशर डिक्रीज हो गया नॉन वॉलेटाइल सॉल्यूट ऐड करने पे। लेकिन हम तो बॉइलिंग पॉइंट की बात कर रहे हैं, और बॉइलिंग पॉइंट में जब वेपर प्रेशर सॉल्यूशन का इक्वल हो जाएगा एटमॉस्फेरिक प्रेशर के, तभी वो बॉइलिंग पॉइंट तक रीच कर सकता है, वो टेम्परेचर ही बॉइलिंग पॉइंट टेम्परेचर कहलाएगा। लेकिन यहाँ पे क्या हो रहा है, जो वेपर प्रेशर है सॉल्यूशन का वो तो डिक्रीज कर गया, लेकिन अब हमें उसको उसके बॉइलिंग पॉइंट तक रीच कराने के लिए, उसको एटमॉस्फेरिक प्रेशर के इक्वल कराने के लिए हमें सॉल्यूशन को हीट करना पड़ेगा, उसे हमें टेम्परेचर प्रोवाइड करना पड़ेगा। ठीक, thus the boiling point of the solution is always higher than that of the boiling point of the pure solvent. इट मीन्स अगर हम टेम्परेचर प्रोवाइड करते हैं तो टेम्परेचर प्रोवाइड करने के बाद जो बॉइलिंग पॉइंट है सॉल्यूशन का वो हमेशा ज्यादा हो जाता है then that of the boiling point of pure solvent in the solution in which the solution is prepared. This can further be seen by a graph, that if we plot the graph between vapor pressure and temperature. So initially we are talking that the vapor pressure of pure solvent, if we are talking about pure solvent, so the vapor pressure of pure solvent is higher, always higher, because only solvent is present in that condition, so vapor pressure of solvent is also always higher. But as we form a solution on mixing a non-volatile solute to that solvent, ठीक है, जो सॉल्वेंट था जिसका वेपर प्रेशर बहुत हाई था, अगर उसी सॉल्वेंट में हम नॉन वॉलेटाइल सॉल्यूट को ऐड करें और हम सॉल्यूशन बना रहे हैं, तो सॉल्यूशन का जो वेपर प्रेशर होगा वो क्या करेगा, डिक्रीज करेगा। तो उसका ग्राफ हम कुछ यहाँ प्लॉट कर सकते हैं। ठीक, तो लेकिन अभी हमने एक चीज डिस्कस करी कि बॉइलिंग पॉइंट वो टेम्परेचर है जहां पे सॉल्यूशन का वेपर प्रेशर और एटमॉस्फेरिक प्रेशर दोनों इक्वल हो जाए। तो इट मीन्स हमें सॉल्यूशन के वेपर प्रेशर को एटमॉस्फेयर के प्रेशर के इक्वल करने के लिए टेम्परेचर प्रोवाइड करना पड़ेगा। एंड एज वी प्रोवाइड द टेम्परेचर टू द सॉल्यूशन, तो जो सॉल्यूशन का बॉइलिंग पॉइंट है वो हायर हो जाता है, किससे, प्योर सॉल्वेंट के बॉइलिंग पॉइंट से। अब देखो प्रेशर, वेपर प्रेशर तो किसका हायर था, यहाँ सॉल्वेंट का हायर था, तो वो टेम्परेचर के साथ इंक्रीज कर रहा है। अब सॉल्यूशन का वेपर प्रेशर सॉल्वेंट के कंपैरिजन में लेस है, बट टेम्परेचर के साथ इंक्रीज कर रहा है ग्राफ। लेकिन हमने टेम्परेचर प्रोवाइड करा सॉल्यूशन को, तो टेम्परेचर जो बॉइलिंग पॉइंट है सॉल्यूशन का वो कहाँ आ जाएगा, हायर होगा। दिस इज द बॉइलिंग पॉइंट ऑफ सॉल्यूशन TB। ये पॉइंट है जहां पे क्या हो रहा है, सॉल्यूशन का जो टेम्परेचर है वो इक्वल हो रहा है एटमॉस्फेरिक प्रेशर के। सो दिस इज द बॉइलिंग पॉइंट ऑफ सॉल्यूशन, दिस पॉइंट, एंड दिस पॉइंट इज बॉइलिंग पॉइंट ऑफ सॉल्वेंट। सो फ्रॉम दिस वी हैव कंक्लूडेड दैट द बॉइलिंग पॉइंट टेम्परेचर of solution is always greater than the boiling point temperature of solvent. ठीक है, this can also be seen by the graph. Here this TB is always has the greater value because it is for solution, it has greater value of temperature. This value of temperature will be greater than this value of temperature, and T naught B is the boiling point temperature for pure solvent. Let T naught be the boiling point of pure solvent and T be the boiling point of solution. The increase in boiling point is known as elevation in boiling point, and that can be denoted as delta TB. Increment in boiling point can be known as elevation in boiling point. It is denoted by delta TB. So from this, the value of delta TB will be equal to TB minus TB naught, where TB is the boiling point of solution which has higher value, and TB naught is the boiling point of pure solvent which has lower value. As we have already discussed in graph that the boiling point of solution has higher value because we have provided the temperature to solution to come to its atmospheric pressure. So the value of TB is higher as compared to the value of boiling point of pure solvent, that is TB naught. So there here delta TB, it is the difference between the boiling point of solution and the boiling point of solvent. As experiments shown that for dilute solutions, the elevation of boiling point delta TB is directly proportional to the molar concentration of the solute in solution. Thus, delta TB will be directly proportional to molality. So, on removing the proportionality sign, we get a constant delta TB will be equal to Kb into molality. And here it is a constant, and that constant is known as boiling point elevation constant. That Kv, which is a constant which get after removing the proportionality sign, and this Kb is known as boiling point elevation constant or molar elevation constant. It is also known as ebullioscopic constant. इसका एक नाम और है और इसको बोला जाता है ebullioscopic constant Kb. Here in equation 2, m is molality, which is the number of moles of solute present in 1 kg of solvent. It is the number of moles of solute present in 1 kg of solvent. Now the unit of Kb is Kelvin, kilogram per mole. From elevation in boiling point, we can also find out the molar mass of solute. If W2 gram of solute of molar mass M2 is dissolved in W1 gram of solvent, then molality M of the solution can be expressed as M molality will be equal to number of moles of solute divided by weight of solvent in grams into 1000. So since number of moles of solute will be equal to mass of solute, which is V2, which is given in grams, which is V2, W2 divided by number of moles of solute, which is also given that is M2. So the molality will be equal to W2 into 1000 divided by M2 into W1. On substituting the value of molality in equation 2, we will get our equation 2 is delta TB will be equal to Kb into molality. So on putting the value of molality in equation 2, we will get delta TB will be equal to Kb into W2 into 1000 divided by M2 into M1 W1. Thus molar mass of solute, that is M2. So from here the molar mass of solute can be calculated. So on rearranging this equation, M2 will be equal to Kb into W2 into 1000 divided by delta TB into W1. So from this, the value of molar mass can be calculated easily by using elevation in boiling point temperature, that is delta TB. And it must be remembered that the elevation in boiling point is a colligative property, but boiling point is not a colligative property. Elevation in a boiling point is a colligative property, but boiling point is not a colligative property. So Elevation in boiling point can be seen by a question. We have a question that 18 gram of glucose C6H12O6 is dissolved in 1 kg of water in a saucepan. At what temperature will water boil at 1.03 bar? Means atmospheric pressure is given. Kb for water is 0.52 Kelvin kg per mole. Since given as mole of glucose, since mass of glucose is given, from this moles of glucose can be find out. Moles of glucose will be equal to 18 upon molar mass of glucose, that is 180. From this moles of glucose comes to be 0.1 mole. Number of kilograms of solvent. Number of solvent is 1 kg. Thus the molarity of glucose solution, molarity of glucose solution will be 0.1 mole per kg. For water, change in volume, change in boiling point delta Tb will be equal to Kb into m, and on putting the value of molality and Kb, we will find the value of delta Tb, that is 0.0052 Kelvin. Since water boils at 373.15 Kelvin at 1 atmospheric pressure, it means 1.013 bar pressure, therefore the boiling point of the solution will be, एडिशन कर देंगे दोनों का, मीन्स जो जिस टेम्परेचर पे वाटर बॉईल हो रहा था प्लस जो हमने डिफरेंस फाइंड आउट किया था, तो हमें तो केवल सॉल्यूशन का टेम्परेचर निकालना है, मीन्स हमें किसकी वैल्यू फाइंड आउट करनी है, डेल्टा टीबी की. तो डेल्टा टीबी क्या हो जाएगा, सॉरी हमें जो वैल्यू फाइंड आउट करनी है, हमें केवल वैल्यू फाइंड आउट करनी है टीबी की. सो टीबी विल बी इक्वल टू डेल्टा टीबी प्लस टीबी नॉट, एंड टीबी नॉट इज temperature of water at which it boils. Temperature of solvent, pure solvent, it means 373.15 plus 0.052 equal to 373.202 Kelvin. These are some practice questions for you. Solve these questions. And this is all for today. We will discuss our next two colligative properties in our next videos. Thank you.